The first step to understanding polar coordinates and polar equations is to learn how to plot polar coordinates on a polar plane. A polar coordinate will have two values, r and theta. Theta will tell us our angle of rotation, and r will be a directed distance along this angle. You can see on our polar plane that we have concentric circles of radius 1, 2, 3, and 4 units. Looking at our first example, r is 2, which lets me know that this point will be lying on the circle with the radius of 2, and our angle of rotation is 2 pi over 3. So let's start by drawing the angle 2 pi over 3. And now our point will be on an r value of 2. Looking at the second example, r is 4, and our angle of rotation is negative pi over 2. So this means we'll be rotating pi over 2 radians, but in the negative or clockwise direction. So our angle of rotation is negative pi over 2, and our point lies on an r value of 4. What might seem a little strange is seeing the next example where we have a negative value for r, because in the past, our convention has been that r is always a non-negative value because it represents the radius of a circle. However, in the polar coordinate system, r is now a directed distance, which means it might take on a negative value, and that just indicates a change in the direction. So let's see what that means, looking at this example. First, we have our angle of rotation, 5 pi over 6. Starting here, I would be at an r value of 0. And if I moved along this ray, I would be at an r value of 1, 2, 3, or 4. Since r is negative 3, I'm going to move in the opposite direction. So starting here at 0, I would move 1, 2, 3 units. So I'm still lying on the circle with the radius of 3, but moving in the opposite direction. In our final example, we have an r value of negative 3 and a theta value of negative 5 pi over 6. So let's start with negative 5 pi over 6, which means we're rotating 5 pi over 6 radians in the negative direction. And now a value of negative 3 for r means we would move 1, 2, 3 units in the negative or opposite direction. Now take a minute to think about another way that we might represent this same point, but using a positive value for r. I might call this point positive 3, and then using an angle of pi over 6. This ordered pair 3 pi over 6 would lie on the same spot as this last example. So you can see that unlike a rectangular coordinate system where each point, it can only be represented in one way, any point on the polar plane can be represented in an infinite number of representations. As we just saw in our last example, there are different ways of representing a point on a polar plane. So let's take, for example, the point 4 pi over 4. We could represent the same point by using an angle that's coterminal to pi over 4. So if I take the angle pi over 4 and add 2 pi, I get an angle 9 pi over 4 that is coterminal to pi over 4. Therefore, the ordered pair 4, 9 pi over 4 would lie on the same spot on the polar plane. I could find any other coterminal angle by continuing to add or subtract any multiple of 2 pi and would still have a point that lies on the same spot on our polar plane. Another way of naming this point, but using a negative value for r, would be to find the angle that forms a line with pi over 4. So if I take pi over 4 and add pi, I find that this angle is 5 pi over 4. The ordered pair -4, 5 pi over 4 would lie in the same spot. 5 pi over 4 would rotate to here, and then a value of -4 would move 4 units in the opposite direction. So in this way, we're able to represent any point in an infinite number of ways. Let's look at an example. We're asked to name 3 different representations of the point 2 pi over 3. You may recall this is the first point that we plotted. In the earlier examples. In our example, the first one that we're asked to find, we're asked to represent it using a value of r that is positive, but a value of theta that lies between -2 pi and 0. So to do that, I need to find an angle that's coterminal to 2 pi over 3, but has a negative value. If we take 2 pi over 3 and subtract 2 pi, we get -4 pi over 3. So -4 pi over 3 is greater than or equal to -2 pi and less than 0, and is coterminal to 2 pi over 3. So we can represent this point as 2 -4 pi over 3. Taking a look at the next example, notice that we're now asked to represent this point using a negative value for r, which means that I need to find the angle that forms a line with 2 pi over 3. To do that, I'm going to take 2 pi over 3 and add pi. Notice that I still want my angle to lie between 0 and 2 pi. So if I take 2 pi over 3 and add pi, I get the angle 5 pi over 3. So I can represent this point as -2, 5 pi over 3. My angle 5 pi over 3 is here. A value of -2 would move 2 units in the opposite direction. Finally, we're asked to find a third representation where we have a positive value for r, but now a value of theta that is greater than or equal to 2 pi, but less than 4 pi. So I need to find the angle that's coterminal to 2 pi over 3, but that lies between 2 pi and 4 pi. If I take 2 pi over 3 and add 2 pi, I get an angle of 8 pi over 3. So the third way that we can represent this point is 8 pi over 3. Now, as we said, there are infinitely many ways that we can represent this point, but all 4 of these representations would result in the same point on our polar plane. In order to convert from polar coordinates to rectangular coordinates, we need formulas that help us relate r and theta to x and y. Luckily, we already know these formulas from previous sections. So look at point P, that's r theta. If we think about this in terms of a right triangle, we have sides x, y, and r. We know that sine theta is equal to y over r. If we take this formula and rearrange it to solve for y, we get y equals r sine theta. We also know that cosine of theta is equal to x over r. Rearranging this formula to solve for x, we see that x is equal to r cosine theta. So these are the two formulas that we will be using to convert from a polar coordinate to a rectangular coordinate. But you should realize that they are not new formulas to you. They're just rearranged into a new form that's more useful for what we're doing here. Looking at our first example, we have the polar coordinate 3, 2 pi over 3, which would be in the second quadrant. You can think about it as being right here. Picture taking a rectangular coordinate plane and lying it on top of our polar plane. We want to find the corresponding point x, y that would be in that same location. To find x, we can use the formula x equals r cosine theta. In this case, r is 3 and theta is 2 pi over 3. Thinking about cosine of 2 pi over 3, we see that it has a reference angle of pi over 3. The angle lies in quadrant 2 where cosine is negative. So the cosine of 2 pi over 3 is negative 1/2. And our x coordinate is negative 3/2. To find the y value for our ordered pair, we use the formula y equals r sine theta. So y is equal to 3 sine of 2 pi over 3. Again, a reference angle of pi over 3. Quadrant 2 where sine is positive. So the sine of 2 pi over 3 is 3 square root of 3 over 2. And so our y value is 3 square root of 3 over 2. And so our rectangular coordinate is negative 3/2, 3 square root of 3 over 2. It's always good to check to see that these 2 points would lie in the same quadrant. So we already established that this point is in quadrant 2. Looking at your rectangular coordinate, we have a negative value for x and a positive value for y. So this point in rectangular form also lies in quadrant 2. Looking at the second example, 7 pi, we could use these formulas in the same way that I did in the first example, and feel free to do that if you're more comfortable with that. However, since the point lies on the x-axis, I can probably figure out the rectangular coordinate even without using the formulas. So let's look at our polar coordinate. Pi means that we would lie on the negative x-axis and an r value of 7. So we would rotate over to pi, and we would move 7 units to the left. So thinking about this in terms of an xy axis, if I move 7 units to the left, then x would be negative 7. And since I'm on the x-axis, the y value is 0. Now again, while you can do this without using the formulas, you could also fill into the formulas just like we did in the first example. In our third example, the first thing I see is that I have a negative value for r and a negative value for theta. While I could just take these and substitute them into the formula as they are, one way that we might make this easier is to rename this using a different representation as we did in previous examples. So let's think about where negative 4, negative 3 pi over 4 would be. Negative 3 pi over 4 would mean rotate 3 pi over 4 radians in the negative direction, which would put me in quadrant 3. An r value of negative 4 would mean I would move 4 units in the opposite direction. So I see that this point is in quadrant 1. I might rename it by taking negative 3 pi over 4 and adding pi, which would give me pi over 4. And so I would rename this point as 4 pi over 4 and use that representation to convert it to rectangular form. Now again, if you did not do this and you used the original representation, you still should get the same answer, but it's just a more complicated problem to figure out. So filling into our formula, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. The cosine of pi over 4 is 1 over square root of 2, and the sine of pi over 4 is also 1 over square root of 2. So our coordinate will be 4 over the square root of 2, comma, 4 over the square root of 2. Now that we've converted from polar to rectangular coordinates, we're going to take a look at converting from rectangular to polar. These first two examples are points that lie on the x or y axis. When that's the case, you don't need a formula to make the conversion. You just need to plot the point and look at where it's located. So let's look at our first point, 0, -1. Keep in mind that we're looking at a rectangular coordinate, so values x and y. To convert it, we're looking for values r and theta. So looking at this as our xy axis, the point 0, -1 would be right here on the negative y-axis. So now thinking about that in terms of a polar coordinate, let's think about the values of r and theta. If I start at 0 and rotate in the positive or counterclockwise direction, theta is 3 pi over 2. Now if you think about our polar plane with the concentric circles, it would lie on a circle with a radius of 1 unit. So our polar coordinate would be 1, 3 pi over 2. Looking at our second example, 4, 0 lies on the positive x-axis. So here's our point 4, 0. Now we need to find r and theta. Since our point lies on the positive x-axis, theta is 0 radians. And then if you think about our circles, this point would lie on a circle with a radius of 4 units. So in polar form, this point would be 4, 0. Now this might seem strange because the rectangular form looks the same as the polar form. It's important to remember that this 4, 0 representing x and y don't have the same meaning that this 4 and 0 has, where it represents r and theta. You also may be thinking about the fact that there are different ways that we could represent any of these points. So you might have thought that it was 4, 2 pi, which would be a correct representation. But the convention is that the directions will specify, in most cases, that you want an r value that's positive and a theta value that's greater than or equal to 0 but less than 2 pi. So while there are infinitely many representations for these points, you will generally be asked to find this particular representation. In our third example of converting a rectangular coordinate to polar coordinate, we now have a point that does not lie on the x or y axis. So we're going to need some formulas that help us relate x and y to r and theta. So looking at our point xy, we want to figure out theta, our angle of rotation, and r. the length of this segment. Drawing in our right triangle, we know x and y, and we can find r by using the Pythagorean theorem, x squared plus y squared equals r squared. Since we're looking for r, we might go ahead and take the square root of both sides and write our formula as r equals the square root of x squared plus y squared. And this is the formula that we will use when converting from rectangular to polar to find r. In this example, x is negative 6 square root of 3, and y is negative 6. When squaring negative 6 square root of 3, remember that both the negative 6 and the square root of 3 need to be squared. So we have negative 6 squared times the square root of 3 squared. Negative 6 squared is 36. The square root of 3 squared is 3. So multiplying 36 times 3, we get 108. Plus negative 6 squared, which is 36. We now have that r is equal to the square root of 144, and so r is 12. Now we need to find theta. So again, recall from earlier sections, how can we relate theta to x and y? And if you think through your trigonometric functions, we would want to use the tangent function. So the formula that we will use to find theta is tan theta equals y over x. Substituting in y and x into our formula, we have tan theta equals negative 6 over negative 6 square root of 3, which reduces to positive 1 over square root of 3. Now we need to solve this trigonometric equation. To do that, we need to find the reference angle. To find the reference angle, we're going to need to find the inverse tangent of the absolute value of 1 over square root of 3. Now in this case it happens to be positive already, but recall that in a case where this is a negative value, you would find the inverse tangent of the positive value. So to find theta r, we will find the inverse tangent of 1 over square root of 3. And that tells me that my reference angle is pi over 6. Looking at our coordinate, I see that my angle needs to be an angle that lies in the third quadrant. So I need to take my reference angle, theta r, which I now know is pi over 6, and add pi to it. So theta will be pi plus pi over 6, which is 7 pi over 6. So now we have our polar coordinate. R is 12, and theta is 7 pi over 6. As a preparation for graphing equations in polar form, we're going to look at how to convert an equation from rectangular form to polar form. To do that, we'll use the same 4 formulas that we've used earlier in this section. And in our rectangular equation, the equation will be in terms of x or y or both, and we will need to rewrite it to be in terms of r or theta or both. In the first example, our equation is x squared plus y squared equals 49. Looking at our formulas, I see that x squared plus y squared is equal to r squared. So therefore, I can replace x squared plus y squared with r squared and rewrite the equation as r squared equals 49. Taking the square root of both sides, I get 2 possible equations, r equals 7 or r equals negative 7. Either of these is an acceptable polar form for this rectangular equation. In the second example, I again want to replace the x's and y's so that they're in terms of r or theta or both. To do this, I'm first going to take the x minus 1 squared and expand it by multiplying x minus 1 times x minus 1. That gives me x squared minus 2x plus 1 plus y squared equals 1. Rearranging my terms on the left-hand side, I can write x squared plus y squared minus 2x, and then if I subtract 1 from both sides, it's now equal to 0. Again, x squared plus y squared is equal to r squared. So I can replace x squared plus y squared with r squared. I see that x is equal to r cosine theta. So I can replace the x with r cosine theta. I now have a polar equation because it's in terms of r and theta. However, the convention for a polar equation is generally to write it in terms of r equals. So I would like to take this equation and solve for r. To do that, I'm going to factor out the common factor of r. So I have r times r minus 2 cosine theta equals 0. Setting each of these factors equal to 0, I get two possible equations. R equals 0, or r minus 2 cosine theta equals 0, which gives me r equals 2 cosine theta. The equation r equals 0 is not necessary to include because r equals 2 cosine theta also includes the r values of 0. So the only equation that we need to express this in polar form is r equals 2 cosine theta. And so that is the polar form of this rectangular equation. In the final example, we have the rectangular equation x equals 9. Again, using the fact that x is equal to r cosine theta, I can replace x with r cosine theta. Solving the equation for r by dividing both sides by cosine theta, I get that r is equal to 9 over cosine theta, which can be written that way, or using one of our reciprocal identities, I could rewrite this as r equals 9 times secant theta. So when converting from rectangular to polar form in an equation, you need to use the formulas that we know that relate x and y to r and theta to rewrite the equation to be in terms of r or theta or both. Now that we've converted equations from rectangular to polar form, we're going to look at how we can use those same four formulas to convert from polar to rectangular form. So now we have equations that are in terms of r or theta or both, and we want to rewrite them to be in terms of x or y or both. Looking at the first example, I have r equals 5. Scanning the formulas, I see that if I had r squared, I could use the third formula, x squared plus y squared equals r squared. So I want to take my equation and square both sides and rewrite it as r squared equals 25. Now I can replace the r squared with x squared plus y squared, and my rectangular form of the equation will be x squared plus y squared equals 25. Looking at the second example, it might make sense at first glance to maybe square both sides again. However, if you look at the right-hand side, if we square this side, we would then have sine squared theta. And if you look at your formulas, you see that we don't really have a formula that we could immediately use if we had sine squared. So instead, we're going to try a little bit different tactic. And we're going to take this equation and we're going to multiply both sides by r. So if I have r equals negative 5 sine theta, and I multiply both sides by r, I see that I have r squared equals negative 5r sine theta. Now I can again replace r squared with x squared plus y squared. And then on the right-hand side, I can replace r sine theta with y. And so I've now written my equation to where each side is in terms of x or y or both. In the third example, I see that it looks very similar to example 2. So again, I might think that multiplying both sides by r would be a good tactic. But again, if you look at the right-hand side, it is now in terms of cosecant. And we only have formulas that help us relate cosine, sine, or tangent functions to x and y. So what we're going to do instead is first use the reciprocal identity for cosecant and rewrite cosecant as 1 over sine theta. Multiplying both sides by sine theta, we have r sine theta equals negative 5. Now I can replace r sine theta with y, and the rectangular form of my equation is y equals negative 5. So when converting from polar to rectangular form, you'll often have to manipulate the equation so that it matches one of your 4 formulas in order to be able to make a substitution. To graph polar equations, it's first helpful to be able to identify the type of graph that will be formed by looking at the structure of the polar equation. The first group of graphs that we're going to examine are polar equations that graph lines. These will be written in one of 4 ways, depending on what type of line it graphs. The first example that we're going to look at is a vertical line. In polar form, an equation in the form r cosine theta equals some constant a will be the graph of a vertical line. So for example, this equation might be r cosine theta equals 9. Thinking back to r cosine theta being equivalent to x, then this makes sense because in rectangular form, this equation would be x equals 9, which we also know graphs a vertical line. An equation in the form r sine theta equals some constant a will be the graph of a horizontal line. So for example, this graph might have an equation r sine theta equals 5. Knowing that r sine theta is equivalent to y, in rectangular form, this equation would be y equals 5, which again, we know graphs a horizontal line on a rectangular plane. If we have a line that is not vertical or horizontal and does not pass through the pole, which on a polar plane means the point 0, 0. So we have a line that is not vertical or horizontal and does not pass through this point 0, 0. Then the equation will be in the form a r cosine theta plus b r sine theta equals c, where a, b, and c are some constants, and a and b are neither 1 equal to 0. So this equation might be in the form 2r cosine theta minus 3r sine theta equals 6. In rectangular form, that equation could be written as 2x minus 3y equals 6. And again, we would be able to recognize that as a line that is not vertical or horizontal and does not pass through the pole. The fourth type of line that we need to consider is a line that again is not vertical or horizontal, but that does pass through the pole and forms an angle alpha with the polar axis. On a polar plane, The polar axis is what we generally think of as the x-axis when we're talking about a rectangular plane. So that's our polar axis. And this line forms some angle alpha. In this case, we can just write the equation in the form theta equals whatever the angle measurement of alpha is. So for example, the equation of this line might be theta equals 5 pi over 6. That would not only represent the points along this ray of 5 pi over 6, but would also represent the points on the other side of the ray that forms a line, because recall that if we start at 0 and we have negative values for r, those would move along the other side of the 5 pi over 6 ray and form the entire line. So these are the 4 forms of polar equations that graph lines. You should be able to recognize them as lines and further be able to describe them as vertical, horizontal, or lines that are not vertical or horizontal that do or do not pass through the pole. Next, we will look at polar equations that graph circles. There are 3 different forms of a polar equation that we will examine, all of which form the graph of a circle. The first type of circle that we'll look at is a circle that's centered at the pole, which means its center is at the point 0, 0, and has a radius that is the length of the absolute value of a. In this case, the equation will be in the form r equals a, where a is some constant. So for example, the equation of this circle might be r equals negative 3. That would tell me that this is a circle that has a center at the pole and that has a radius of 3 units. The second type of equation that we'll look at is an equation in the form r equals a sine theta. An equation in this form will also graph a circle. The circle will be centered on the line theta equals pi over 2, which would be on the y-axis if we were talking about a rectangular coordinate system. The center will be the absolute value of a over 2 units from the pole, and the length of the radius will be the absolute value of a over 2 units. So for example, the equation of this circle might be r equals negative 4 sine theta. In this case, I would know that this is a circle that's centered on the line theta equals pi over 2. The center will be the absolute value of a, which is negative 4 over 2 units from the pole. So the center will be 2 units from the pole, which means that the center would be at the point 0, negative 2. The radius will be a length of absolute value of a over 2 units. So the radius is 2. The reason that the center was on 0, negative 2 instead of 0, positive 2 is because this coefficient in front of sine theta was a negative 4. Had it been a positive 4, we would have gone through the same procedure, except that the center would be 2 units above the pole instead of 2 units below. The third form of a circle that we're going to examine would be an equation in the form r equals a cosine theta. In this case, the circle will be centered on the polar axis, which recall that means the x-axis when we're talking about a rectangular plane. And again, the center will be the absolute value of a over 2 units from the pole, and the radius will have a length of the absolute value of a over 2. So an equation for this circle might be something like r equals 2 cosine theta. R equals 2 cosine theta would be a circle that's centered on the polar axis. Its center would be the absolute value of a over 2 units away from the pole. So its center would be 1 unit from the pole, which means that the center would be at the point 1, 0, and its radius would be 1. So given an equation in any of these 3 forms, you should be able to recognize that it's a circle and be able to determine the center and the radius of the circle. The next type of graph that we're going to look at is the graph of a limacon. The equation will be in one of 2 forms, r equals a plus b sine theta, or r equals a plus b cosine theta. Once you've identified that the graph will be a limacon, you need to consider one of 4 cases by looking at the absolute value of a divided by b. The absolute value of this ratio will tell you a little bit more about the shape of the limacon. If the absolute value of a over b is less than 1, then the limacon will have an inner loop. So it will have both an inner loop and then this larger outer loop. As this ratio increases towards the value of 1, the inner loop will become smaller and smaller. If the ratio of a over b has an absolute value that is exactly equal to 1, then the inner loop disappears and the graph forms what is called a cardioid. And instead of having an inner loop, it has this sharp turn or cusp in the graph. If the ratio increases beyond 1 to any value between 1 and 2, then this sharp turn or cusp begins to disappear or become less pronounced. And as the absolute value of a over b increases from 1 to 2, the graph will be a limacon that will have this dimple. So it still has this turning point, it's just not as sharp or pronounced. And again, as the ratio approaches 2, this dimple will become smaller and smaller or less pronounced. Once the absolute value of a over b is exactly equal to 2, that dimple then disappears. And the graph looks almost like a circle, and you can see on my drawing that it looks very much like a circle. You have to look closely to see that there's this part that looks almost vertical. It's not completely vertical, it does not completely flatten out, but it has this part that is very steep, and so this graph is not exactly a circle, but it does look very similar to a circle. So once the absolute value of a over b reaches a value of 2 or greater, you will have a limacon, but it will have no inner loop or dimple. So that ratio can tell you quite a bit about the graph. Whether the equation is in terms of sine or cosine can also give you a little bit more information about the symmetry of the graph. If the graph is in terms of cosine, in the form r equals a plus b cosine theta, then the graph will be symmetric along the polar axis. So you see that all 4 of the graphs I have drawn here are symmetric with respect to the polar axis. So all 4 of these graphs would have equations in the form r equals a plus b cosine theta. If the equation is instead in terms of sine theta, then the graph will be symmetric with respect to theta equals pi over 2, which we'll look at an example in a minute. In this example, I see that the equation is in the form r equals a plus b sine theta, which tells me that the graph is going to be a limacon. Looking at the absolute value of the ratio a over b, it's equal to the absolute value of 1 over negative 2, which is 1/2. Since 1/2 is less than 1, this graph is going to be a limacon with an inner loop. Because the equation is in terms of sine, I know that the graph will be symmetric about the line theta equals pi over 2. Now that I know a little bit about what the graph is going to look like, I want to select some values to substitute in for theta to get some points to plot. The values that I'm going to use for theta are the quadrantal angles, because they are easy to figure out and often represent the important points on the graph. And then I'm going to use the angles in the pi over 6 family. The reason I'm using pi over 6 angles is because this equation is in terms of sine, and I know that the sine of pi over 6 is 1/2. Had the equation been in terms of cosine, I would have used the quadrantal angles and the angles in the pi over 3 family. While any angles that you choose will work, these are the best angles to choose in this case. So I'm going to use the values of theta starting with 0, then pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, and 11 pi over 6. I could finish with 2 pi, but when I substitute in 2 pi, I'll get the same value as when I substitute in 0. Starting with 0, r will equal 1 minus 2 times the sine of 0. Since the sine of 0 is 0, r will end up equaling 1, and I'll have the ordered pair 1, 0, r theta. Substituting in pi over 6, the sine of pi over 6 is 1/2. 2 times 1/2 is 1. 1 minus 1 gives me 0. So I have the point 0 pi over 6. Continuing with pi over 2, the sine of pi over 2 is 1. 2 times 1 is 2. 1 minus 2 gives me a value of -1. Five pi over 6 is in the pi over 6 family, so I know that the sign will be either positive or -1/2. Since 5 pi over 6 is in quadrant 2, sine of 5 pi over 6 is +1/2, which means it will work out to be the same value as substituting in pi over 6. So I get an r value of 0. Pi lies on the x-axis, so sine is 0, just like it was when I substituted in 0, which means I will get an r value of 1. Now let's substitute in 7 pi over 6. 7 pi over 6 is in quadrant 3, where sine is negative. So the sine of 7 pi over 6 is -1/2. So I end up with 1 plus 1, or 2. So my point will be 2, 7 pi over 6. 3 pi over 2 is on the negative y-axis. So sine is -1. So I end up with 1 plus 2, or an r value of 3. Eleven pi over 6 is in quadrant 4, where sine is also negative. So 11 pi over 6 will work out in the same way that 7 pi over 6 did and give me an r value of 2. And then again, if I wanted to finish up with 2 pi, I would get a value of 1 again. All right, so now let's plot these points and see what the graph is going to look like. Plotting the first point at 1, 0, I have a point here. 0 pi over 6, so my angle of rotation is pi over 6, but my r value is 0, so the point will be at the pole. My third point is at -1 pi over 2. So recall that if I go to pi over 2, and r is -1, I plot the point 1 unit in the opposite direction from pi over 2, so it would be there. 0, 5 pi over 6. Here's 5 pi over 6. But again, the point is at the pole. 1 pi would be here. 2 7 pi over 6. So here's my 7 pi over 6 angle, and it will lie on the circle with a radius of 2. 3 pi over 2 would be here. 2 11 pi over 6. And then if I circled all the way around, I would end at 1 2 pi. So the graph would start here at this first point, and then the points would be connected in the order of our angles of rotation. So I would go from here to the point on the pole, or the point at the pole, rotate down to form the inner loop, back up through the pole, and then around to form the outer loop. And so, as we said from the beginning, we end up with a limacon that has an inner loop and is symmetric about the line theta equals pi over 2. If the graph happens to be a different type of limacon, such as a cardioid or a limacon that has a dimple, or one that has neither an inner loop nor a dimple, the process of graphing is exactly the same. So once you've identified the type of limacon and the type of symmetry, then it's just a matter of finding enough points to plot to draw the graph. The next type of graph that we're going to look at are graphs of roses. The equation for the graph of a rose will be in the form r equals a sine n theta, or r equals a cosine n theta, where n is a whole number not equal to 1. When n is odd, the rose will have n petals. In this case, you will only need to find points in the interval 0 to pi. After that, if you continued finding points from pi to 2 pi, the graph would simply trace over the petals that you've already located. So in this instance, when n is odd, the graph has n petals, and you need points on the interval from 0 to pi to complete the graph. If n is even, then the rose will have 2 n petals. In that case, you will need to find points on the interval 0 to 2 pi in order to complete the graph. So if n is even, the graph will have twice n, or 2n petals, and you will need to find points from 0 all the way to 2 pi in order to complete the entire graph. In either instance, the length of the petals will be equal to the absolute value of a. So this will tell you how long each of the petals is in length. Now let's look at an example of how to graph a rose. Looking at this example, I can see that this is going to graph a rose because the equation is in the form r equals a sine n theta. N in this case is 5, and since n is odd, the graph will have n petals. So this is a rose with 5 petals. The length of each petal will be 3. And when I say that the length of the petal is 3, I'm referring to the distance from the pole to the outermost endpoint of the petal. So you can see that what we're about to do is find the endpoints of the petals. To do that, we need to know that that length from the pole to the endpoint has to be 3. So to find the endpoints of the petals, we need to find the values of theta, where r is equal to 3, which would be the largest possible value of r. So I could set up this equation, 3 sine 5 theta equals 3. And I'm going to solve this equation for theta. The other possibility is that r could have a value of negative 3. So I also need to set up an equation, 3 sine 5 theta equals negative 3. So when r has a value of 3 or negative 3, those will tell me the values of theta where the endpoints of the petals occur. To solve this equation for theta, I first need to divide both sides by 3. And so we get sine of 5 theta equals 1. Often you'll see that people might skip this first step of setting the equation equal to the largest and smallest possible values of r. And if after a few examples you want to just jump ahead to this step, that's fine. All right, so now I'm solving this trig equation, which means my next step is to undo the sine function and write the general formula that's equal to 5 theta. So I need to think about what angle has a sine value of 1, which is pi over 2. So 5 theta is equal to pi over 2 plus 2 pi k. That's my general formula. I now need to finish solving for theta by dividing by 5. And I get that theta is equal to pi over 10 plus 2 pi over 5 times k. Now I begin substituting in values of k, integer values beginning with 0. So starting with a value of 0, if I substitute in 0 for k, I get that theta is pi over 10. Next, I would want to substitute in 1 for k. Substituting in 1, I would have pi over 10 plus 2 pi over 5 times 1, so just 2 pi over 5. Rewriting this as 4 pi over 10, I get that theta is equal to 5 pi over 10, which reduces to pi over 2. So this is the value I got when I substituted in 0 for k, then 1, and now I'm going to substitute in 2 for k. Substituting in 2, I get pi over 10 plus 2 pi over 5 times 2, which would be 4 pi over 5. Changing 4 pi over 5 to 8 pi over 10, I get a k value of, a theta value of 9 pi over 10 when k is 2. Remember that because n was odd and there were n petals, 5 petals, I only need to find values on an interval from 0 to pi. Therefore, I can stop substituting in values here because if I substituted in 3 for k, I would get a value that exceeds pi. If you're not sure, then you can continue substituting in values, but once you get a value that exceeds pi, you stop. So I now have endpoints for 3 petals, but remember that we have 5 petals. So to get the other 2, I will need to solve this equation for theta using this same process. Dividing both sides by 3, I get sine 5 theta equals negative 1. Now we need to think about the angle that has a sine value of negative 1, and again write our general formula that's equal to 5 theta. Sine equals negative 1 on the negative y-axis, so at 3 pi over 2 plus 2 pi k. Dividing both sides by 5, I get that theta is equal to 3 pi over 10 plus 2 pi over 5 k. Now we're going to do the same thing that we did over here, which is begin by substituting in 0 for k. When k is 0, theta is 3 pi over 10. When k is 1, remember that this will become 4 pi over 10. So 3 pi over 10 plus 4 pi over 10 will give me 7 pi over 10. And I can stop there because I know that there are 5 petals, and I've now found 5 values for theta. So going back and writing these as ordered pairs, you would have an R value of 3 and a theta value of pi over 10, pi over 2, and 9 pi over 10. So let's list these ordered pairs. As I list them, I'm going to list them in order of theta, going in ascending order. So my first ordered pair would be 3 pi over 10. Then my second ordered pair would be negative 3, 3 pi over 10. The next one would be 3 pi over 2. Negative 3, 7 pi over 10. And then the fifth one would be 3, 9 pi over 10. Now let's find the values of theta where the graph crosses through the pole. To do this, we're going to take our equation and replace r with 0. So we're finding the values of theta where the r value is 0. To do this, we're going to solve this trig equation, 3 sine of 5 theta equals 0. Dividing both sides by 3, I get sine of 5 theta equals 0. Now again, I need to undo the sine function and set up the general formula that's equal to 5 theta. Here, you need to think about the fact that there are 2 places where sine equals 0, and they are separated by pi. Sine equals 0 at 0 and pi. So we can write this using just a single general formula. Be 5 theta equals 0 plus pi k. That takes care of 0, and then pi, 2 pi, 3 pi, etc. Now finish solving for theta by dividing both sides by 5. 0 divided by 5 is still 0, so I could write this general formula as just pi over 5 times k. Now again, I would begin substituting in values of k beginning at 0. So the first value would be theta equals 0 when k is 0. Then I would substitute in 1, which would just give me pi over 5. Substituting in 2 would give me 2 pi over 5. Substituting in 3 would give me 3 pi over 5. And then 4 would give me 4 pi over 5. If I substitute in 5, I would get pi, which would complete the graph. But I only need to find interval or points on the interval starting from 0 and up to but not including pi. Now that we have the endpoints of the petals and we know the values of theta where the graph crosses through the pole, we can construct the graph. So we know that at 0, r is 0. Then we can plot the endpoint of the first petal at 3 pi over 10, which would be about right there. These values let me know that the graph keeps crossing back through the pole to form each petal. So even though these points won't be visible because each one has an r value of 0, we know that the graph continues to loop back through the pole as we draw each petal. So let's plot the endpoints of the other 4 petals. The second one will be at -3, 3 pi over 10. So if 3 pi over 10 is about right there, then -3 means we're moving 3 units in the opposite direction, and there's our second endpoint. The third endpoint will be at 3 pi over 2. Then we have an endpoint at -3, 7 pi over 10, which will be 3 units in the opposite direction from 7 pi over 10. And then the fifth endpoint will be at 3, 9 pi over 10. So we can draw the graph now by starting at 0. The graph will loop through the endpoint of the first petal and back through the pole, down to form the second petal, back up through the pole and up to form the third petal, back down through the pole to form petal 4, and then finally loop back through and form the fifth petal. In a case where you have an N value that is even and you have twice as many petals, the process is exactly the same as what you've seen here, as far as finding the endpoints by solving these equations and finding the values of theta where the graph crosses through the pole. The only difference will be that you'll need to find points on the interval from 0 all the way to 2 pi, rather than on the interval from 0 to pi like we did here. The final type of graph that we're going to look at is the graph of a lemniscate. The equations will be in the form r squared equals a squared times sine 2 theta, or r squared equals a squared cosine 2 theta. So you can see that the equations are easy to differentiate from the other ones we've seen today because they look quite different. If the equation is in the form of, or in terms of sine, then the graph will look like this. It will be symmetric about the pole, and the graph will lie on this line, theta equals pi over 4. So it will be symmetric about this line, theta equals pi over 4. If the graph is in terms of cosine, then that graph is also symmetric about the pole, but then it's symmetric about the polar axis. So if the graph is in terms of cosine, your graph will look like this. And if the graph is in terms of sine, it will look like this. For example, r squared equals 36 times sine 2 theta. By looking at this equation, I would know right away that it was a lemniscate and that it's symmetric along this line, theta equals pi over 4. Additionally, I could find the length from the pole to the end point. The length from the pole to the end point of each loop is equal to the value of a. So in this equation, a squared is 36. A is 6. And so the length from the end point of the loop to the pole is 6 units. And the same would be true here. So you can see that in the graphs that we've looked at today, some of the graphs could be easily graphed using our more familiar rectangular graphing system, the graphs of lines and circles. But the other types of graphs we've explored, the limicons, roses, and lemniscates, are much easier graphed using the polar coordinate system than if we converted them to rectangular form and tried to graph them in that way. So each graphing system is useful depending on what type of graph you're trying to generate.
A unit vector is a vector with magnitude 1. We are particularly interested in two specific special unit vectors, I and j. Let's take a moment to talk about notation. A vector written by hand has an arrow over it to show that it is a vector. And note that when you see a vector typed, it's boldface. So the vector I is a unit vector traveling along the x-axis that is exactly 1 unit long. Component representation will be 1, 0. The unit vector j is traveling along the y-axis, and its components are 0, 1. Any vector v in standard position can be written in terms of the unit vectors I and j. Starting with a vector v in standard position with its terminal point AB, then this is the same as having A copies of I plus B copies of j. So we can write that the vector v with components A and B is the same as AI plus BJ. Note that its magnitude will still be the square root of A squared plus B squared. This third representation of the vector v is particularly useful for algebraic manipulation. In this example, we're asked to calculate or find the unit vector u in the same direction as the vector v equals negative 3i plus 5j. We can find this unit vector by dividing our given vector by its magnitude. So let's calculate the magnitude of the vector first. The formula is the square root of a squared plus b squared. So the magnitude of our vector is the square root of 34. Of course, you want to check to see if that can be simplified. Now we're ready to calculate the vector u. The unit vector in the same direction as v, having magnitude 1 to make it a unit vector, is going to be the vector v divided by its magnitude. And we've just calculated that the magnitude is the square root of 34, and we'll separate this so that we can see the components a and b. Let's look at this vector v drawn in standard position. Its terminal point is at AB, so I've written vector v in terms of its components and in AI plus BJ form. Using this picture, we can get several relationships between A, B, and the angle theta. First, let's look at the cosine of theta. The cosine of theta is the adjacent side, which is A, over the hypotenuse of the triangle we see. How long is the hypotenuse? It's exactly the length of the vector, or its magnitude. Rearranging, we obtain this first relationship. A is the magnitude of the vector times the cosine of this angle theta. Now, what about sine of theta? Sine theta is the opposite side B over the hypotenuse. The hypotenuse is the magnitude of our vector. And rearranging this one, we come up with the second relationship. Now let's talk a little bit more about theta. Theta is very special. It's called the direction angle of the vector. We're defining it to be a positive angle formed between the positive x-axis and the terminal side of our vector. Theta has to satisfy this equation. the tangent of theta, it should be the opposite over the adjacent. That would be b over a, where a is not 0. Notice that we've drawn our angle, our vector, so that theta lies in quadrant 1. We can easily extend this to any positive direction angle theta using our general angle definitions of the trig functions. In this example, we're asked to find the direction angle for this given vector. We'll start by drawing the vector in standard position. A is -6, so we go 6 units to the left. B is positive 6 square root of 3, so that is up 6 square root of 3 units. And then we draw our vector so that this is its terminal side. The direction angle theta will be this positive angle between the positive x-axis and our vector that was drawn in standard position. We know that this angle has to satisfy tangent of theta equals b over a, where a is not 0. Because the terminal side of our angle is not in quadrant 1, we will use a reference angle to find theta. The reference angle is the inverse tangent of the absolute value of b over a. Remember that a reference angle needs to be positive and acute, so the absolute value is important here. B is 6 square root of 3, a is -6. Reducing this and taking the absolute value, we're looking for the inverse tangent of the square root of 3. This is a special angle. We should know the value of this. The inverse tangent of square root of 3 is the angle pi over 3. Okay. Now, to use this to find theta. The reference angle is here. So theta is 180 degrees. So we should choose radians or degrees. Pi over 3 is 60 degrees, and then we'll write this one in degrees. In this example, we're given a direction angle of 330 degrees and a magnitude 10 of a vector v, and we're to write this in terms of I and j. That means we need to calculate a and b, the components of the vector. Recall that we know that the relationship between a, b, theta, and the magnitude of the vector, there are two of those. The horizontal component a is the magnitude of the vector times the cosine of the direction angle. And then the vertical component of the vector is the magnitude of the vector times the sine of the direction angle. Substituting what we're given, magnitude of 10, direction angle 330 degrees. We need to calculate these two values. So let's talk about 330 degrees for a moment. The terminal side of 330 degrees is in quadrant 4. The reference angle will be 30 degrees. We know that in quadrant 4, the cosine of an angle is positive. So this will be 10 times the positive cosine of our reference angle. The cosine of 30 degrees is square root of 3 over 2. And we're going to simplify that. Okay. Now, on this one, 330 degrees is still in, terminal side still in quadrant 4. Reference angle is still 30 degrees. But in quadrant 4, the sine of an angle is negative. So this is negative sine of 30 degrees. The sine of 30 degrees is 1/2. Simplifying that, we find that b is -5. Now we have to write this in ai plus bj form. Continue to practice these examples until you've learned to do them by yourself without help of any sort.